Table 450.3 Note 2 of the National Electrical Code addresses when secondary protection is required for electrical equipment installed in locations where the risk of physical damage is significant. A common rule of thumb used to determine whether secondary protection is necessary is the 4:1 ratio method. This method assumes that if a fault occurs on the line side of the overcurrent protection device, the ratio of the available short-circuit current, or ISC, to the interrupting capacity of the device, or IC, should not exceed 4:1. The formula for this is ISC divided by IC is less than or equal to 4, where ISC equals available short-circuit current and IC equals interrupting capacity of the overcurrent protection device. However, it's important to note that Table 450.3 Note 2 does not explicitly specify the 4:1 ratio method. It only states that secondary protection is required where the risk of physical damage is significant. Therefore, it is recommended to consult additional criteria when determining the need for secondary protection. These criteria include the location of equipment. Is the equipment installed in an area where it could be subjected to impact, vibration, or other physical damage? Consider also the construction of the equipment. Is the equipment designed to withstand the potential physical hazards in the location? Also consider the available short-circuit current. Is the available short-circuit current at the location high enough to pose a significant risk of damage to the equipment? In conclusion, while the 4:1 ratio method can be a useful guide, it should not be the sole criterion for determining the need for secondary protection. A more comprehensive evaluation of the potential physical damage risks and other factors is necessary to ensure the safety and protection of electrical equipment. Let's delve deeper into the specifics of applying Table 450.3 Note 2 and the 4:1 ratio method, exploring the nuances and practical considerations that electrical professionals encounter in the field. Understanding the available short-circuit current, or ISC, is crucial. This value represents the maximum current that a circuit can deliver under fault conditions. It's determined by the source impedance, which includes the utility transformer impedance, conductor impedance, and any other impedances in the fault path. A higher ISC indicates a greater potential for damage during a fault. The interrupting capacity, or IC, of the overcurrent protection device, such as a circuit breaker or fuse, represents the maximum short-circuit current that the device can safely interrupt without failing. It's imperative that the IC of the protective device is adequate for the available ISC at its location. The 4:1 ratio serves as a safety margin. By ensuring that the ISC divided by IC is less than or equal to 4, you're aiming to prevent the overcurrent protection device from being subjected to currents beyond its interrupting capability. This helps maintain the integrity of the device and prevents catastrophic failure during a fault. When assessing the location of the equipment, consider factors such as exposure to mechanical impact from moving machinery or vehicles, vibration from nearby equipment, potential for water or chemical exposure, and the presence of combustible materials. Equipment installed in areas with these hazards is more likely to sustain physical damage, necessitating secondary protection. The construction of the equipment plays a significant role in its ability to withstand physical hazards. Equipment designed with robust enclosures, reinforced components, and vibration isolation features is better equipped to withstand physical stresses. Consult the equipment's specifications and certifications to determine its suitability for the intended environment. While the 4:1 ratio provides a quantitative assessment, it's essential to incorporate qualitative judgment based on the specific circumstances. For instance, if the available ISC is relatively low and the equipment is installed in a well-protected environment, secondary protection may not be warranted, even if the 4:1 ratio is slightly exceeded. Conversely, if the available ISC is high and the equipment is exposed to significant physical hazards, secondary protection may be necessary, even if the 4:1 ratio is met. It's also important to consider the coordination of overcurrent protection devices. Selective coordination ensures that the overcurrent device closest to the fault trips first, minimizing the extent of the outage and preventing unnecessary disruption to other parts of the electrical system. When applying the 4:1 ratio method, verify the accuracy of the available ISC and IC values. Obtain the ISC data from the utility company or perform a short-circuit study using appropriate software. Ensure that the IC ratings of the overcurrent protection devices are clearly marked and comply with relevant standards. Consulting with a qualified electrical engineer or inspector is highly recommended, especially in complex or borderline cases. These professionals can provide valuable expertise and guidance to ensure that the secondary protection scheme is appropriate for the specific application. Beyond the 4:1 ratio and the factors outlined in Table 450.3 Note 2, other considerations may influence the need for secondary protection. These include the criticality of the equipment, the potential consequences of a failure, and the insurance requirements of the facility. Critical equipment that is essential for maintaining operations or safety may warrant secondary protection, even if the risk of physical damage is relatively low. The potential consequences of a failure, such as downtime, property damage, or injury, should be carefully weighed when determining the appropriate level of protection. Insurance companies may have specific requirements for secondary protection based on the type of equipment, the location, and the occupancy of the building. These requirements should be taken into account when designing the electrical system. It's important to document the decision-making process for determining the need for secondary protection. This documentation should include the available ISC and IC values, the assessment of physical hazards, the rationale for the chosen protection scheme, and any relevant calculations or studies. Maintaining accurate and up-to-date documentation is essential for demonstrating compliance with the National Electrical Code and for facilitating future inspections and maintenance. Regularly inspect and maintain the electrical equipment and protective devices to ensure their continued functionality. Inspections should include visual checks for physical damage, verification of proper operation, and testing of protective functions. Maintenance should include cleaning, lubrication, and replacement of worn or defective components. Keeping up to date with the latest revisions of the National Electrical Code and industry best practices is crucial for electrical professionals. The NEC is updated every 3 years, and these updates often include changes to the requirements for secondary protection. By staying informed, you can ensure that your electrical systems are designed and installed in accordance with the latest safety standards. Applying Table 450.3 Note 2 and the 4:1 ratio method requires a comprehensive understanding of electrical principles, short-circuit analysis, overcurrent protection, and risk assessment. By considering all relevant factors and consulting with qualified professionals, you can ensure the safety and reliability of electrical equipment and systems. Remember that the goal is to protect equipment and personnel from the hazards of electrical faults, and secondary protection is a valuable tool for achieving this goal. Furthermore, let's examine the practical application of these principles in various scenarios. Consider a transformer installed in a manufacturing facility supplying power to critical production equipment. The transformer is located in an area with heavy machinery and potential for mechanical impact. The available short-circuit current at the transformer's secondary terminals is relatively high. In this scenario, a comprehensive assessment would likely indicate the need for secondary protection. The high available short-circuit current, coupled with the potential for physical damage, poses a significant risk to the transformer and the connected equipment. Secondary protection, such as fuses or circuit breakers, would help to limit the damage in the event of a fault. On the other hand, consider a small control transformer installed in an office building, supplying power to a lighting control system. The transformer is located in a clean, dry environment with minimal risk of physical damage. The available short-circuit current at the transformer's secondary terminals is relatively low. In this scenario, secondary protection may not be required. The low available short-circuit current and the lack of significant physical hazards may not warrant the additional cost and complexity of secondary protection. However, it's still important to perform a thorough assessment and document the decision-making process. In some cases, the installation of a ground fault protection system may be an alternative to secondary protection. A ground fault protection system detects and interrupts ground faults, which are a common type of electrical fault. Ground fault protection can help to reduce the risk of electrical shock and fire, and it may be required by the National Electrical Code in certain applications. When selecting overcurrent protection devices for secondary protection, it's important to consider the device's characteristics such as its interrupting capacity, time current curve, and voltage rating. The interrupting capacity must be adequate for the available short-circuit current at the device's location. The time current curve should be coordinated with other overcurrent protection devices in the system to ensure selective coordination. The voltage rating must be appropriate for the system voltage. Proper installation and maintenance of overcurrent protection devices are essential for their reliable operation. Devices should be installed in accordance with the manufacturer's instructions and the National Electrical Code. Regular inspection should be performed to check for physical damage, corrosion, and loose connections. Devices should be tested periodically to verify their proper operation. When performing electrical work, always follow safe work practices and use appropriate personal protective equipment. Energize and lock out equipment before working on it. Use insulated tools and equipment. Wear appropriate clothing and footwear. Never work alone. By following these safety precautions, you can minimize the risk of electrical shock and injury. In addition to the technical aspects of secondary protection, it's also important to consider the economic aspects. Secondary protection adds to the initial cost of the electrical system. However, it can also reduce the long-term costs associated with equipment damage, downtime, and repairs. A cost-benefit analysis can help to determine whether secondary protection is justified in a particular application. The cost of secondary protection should be weighed against the potential savings from reduced equipment damage, downtime, and repairs. In some cases, the cost of secondary protection may be relatively low compared to the potential cost of a failure. In other cases, the cost of secondary protection may be relatively high compared to the potential savings. A cost-benefit analysis can help to make an informed decision. In summary, determining the need for secondary protection requires a comprehensive assessment of various factors, including the available short-circuit current, the interrupting capacity of overcurrent protection devices, the location and construction of equipment, and the potential consequences of a failure. While the 4:1 ratio method can be a useful guide, it should not be the sole criterion for determining the need for secondary protection. By considering all relevant factors and consulting with qualified professionals, you can ensure the safety and reliability of electrical equipment and systems.